Welcome back to another Visual Computing Labs tutorial. Today we're looking at ordinal patterns and complexity in time series analysis. This tutorial introduces the concepts of permutation entropy and statistical complexity for analyzing time series dynamics. We will learn how to map continuous data into discrete ordinal patterns and quantify structural complexity using Python. To put it simply, instead of just looking at raw numbers, we're going to look at the order and shapes inside our data to spot hidden structures. Let's jump right into task 1. Define the Shannon entropy function. We need a helper function to calculate the standard Shannon entropy of a probability distribution. This will serve as a foundation for our complexity and permutation entropy metrics. Before we look at the code block, let us look at the math behind it. h of x equals the negative sum from I equals 1 to n of p of x sub I times the log of p of x sub I. This formula tells us that to find the total entropy h of x, we take each of the probability p of x sub I in our distribution, multiply it by its own logarithm, sum those values all together, and then flip the sign to positive using that negative sign out front. We start by importing numpy as np and the math module. Then we define our function s underscore entropy, which takes a list of frequency lists. Inside the function, the first line uses a list comprehension to filter out any zeros, because trying to take a logarithm of 0 would cause a math error. Next, we set sh entropy at 0. We loop through each frequency in our list. For each one, we multiply the frequency by its own natural logarithm using np.log and add that to our running total. Finally, because the formula for Shannon entropy has a negative sign in front of the summation, we make the final value negative, and then we return sh underscore entropy. Right below that, we have a quick test case to check our work. We are calculating the entropy for an equal probability distribution with 4 elements, each at 0.25. Since this represents maximum uncertainty, running this cell gives us a Shannon entropy of about 1.386. Now we have our Shannon entropy helper function ready, we need to implement the core of permutation entropy, extracting the ordinal patterns from our time series data. But what exactly is an ordinal pattern? Let's pause the code for a moment and look at what's actually happening under the hood. If you look at the left side of the screen, we have a raw time series graph. To analyze the structure, we use a moving window. In this example, our embedding dimension, or window size, is set to 3. Inside this specific window, we capture 3 consecutive data points with the raw values, 10, 30, and 20. Instead of keeping those raw numbers, permutation entropy converts them into an ordinal pattern based on their relative ranks. 10 is the lowest value, so it gets a rank of 0. 20 is the next highest, getting a rank of 1, and 30 is the highest, getting a rank of 2. So our raw values of 10, 30, 20 translates cleanly into the ordinal pattern 0, 2, 1. Down at the bottom, you can see how any combination of 3 points will always map to one of these unique states, whether it's strictly increasing, strictly decreasing, or fluctuating up and down. So why go through all of this trouble? Why is this step absolutely crucial for modern data analysis? If we rely on traditional statistical metrics like mean or variance, we completely ignore the temporal sequence. Traditional stats treat our data like a bag of random numbers, losing the time-dependent structure entirely. Ordinal analysis, on the other hand, is dynamical. It specifically captures sequence dynamics and quantifies structural complexity. Because it only cares about the relative order of points rather than their exact values, this method is incredibly robust against background noise and doesn't require heavy processing. This makes it a perfect tool for analyzing non-stationary data from complex, chaotic systems, creating highly resistant features for machine learning models, and running real-time performance tracking without heavy computational overhead. Now let's turn what we just learned into Python code. We start by defining our main function, ordinal patterns, which accepts our time series data along with our embedding dimension and delay parameters. For our convenience, we assign these parameters to the shorthanded variables m and t. Next, we ensure our input data is in a format optimized for speed. If the time series isn't already in a numpy array, we cast it into one. To prepare our vector space, we initialize a temporary matrix of zeros called temp. This shape determined by the total length of our time series as rows and our embedding dimension m as columns. We use the for loop to iterate our window size m. In each iteration, we use the roll function to shift the entire time series over. By stacking these shifted versions side by side into columns, we instantly create all of our overlapping sequences at once. So that was a lot that we just covered. Let's take a step back. I'm going to put on screen an example. We're going to use some real numbers to go through exactly what we just did. We start by setting up a NumPy array containing elements 10, 20, 30, 40, and 50. And just like before, we set our window size m to 3 and our step delay t to 1. Next, we initialize an empty matrix of zeros called temp with 5 rows and 3 columns. Now watch exactly what happens when we run our loop. It's going to iterate exactly 3 times, building our matrix column by column. In the first iteration, where I equals 0, there is no shift. The original array is placed cleanly into column 0. In the second iteration, where I equals 1, the function shifts our entire array down by 1 position. The 50 at the bottom loops right around to the top, filling column 1 with 50, and then 10, 20, 30, 40. In the final iteration, where I equals 2, the array shifts down by 2 positions, so we have 40 in the first position and 50, and then 10, 20, 30. Now take a look at our outputs. Look at the rows horizontally. By simply shifting the data vertically, NumPy has instantly lined up every single chronological overlapping window we need, completely eliminating the need for a slow manual slicing loop. Once we have sorted our time series data segments into permutation patterns, the next step is to quantify how often each pattern occurs. First, we pass in our sorted permutations into a helper function called _hash. This converts each unique ordinal pattern into a specific single integer index. Think of it like giving every unique sequence its own ID number. Next, we initialize an array of zeros called counts. The size of this array is exactly the factorial of our embedding dimension, which represents the total number of possible patterns that could ever exist. Then, a quick loop runs through every single possible index. It counts up how many times our calculated indices match the current pattern ID, filling our array with the exact frequency of each pattern. And lastly, the function cleans things up. It filters out any patterns that never showed up in our data, converts remaining frequencies into clean integers, and returns them as list. We now have the raw pattern counts ready to measure the complexity of our time series. Let's look at a quick example here. We have a time series data that rises from 10 to 30 and then drops back down to 0. We set the embedding dimension to 3 and delay to 1. This means the algorithm will analyze the data by looking at groups of 3 consecutive points at a time. When we print the results, it detects a total of 3 unique ordinal patterns. The initial upward trending pattern is detected twice, while the peak pattern and the purely decreasing downward pattern appears exactly once each. With these distribution counts captured, we now have the exact blueprint we need to calculate the structural complexity and entropy of our time series. Now, before we get into task 3, calculating permutation entropy, it is important to understand how permutation entropy differs from standard Shannon entropy, like what we built in task 1. Standard Shannon entropy looks strictly at frequencies of individual values or states, completely ignoring the chronological order of the data. Permutation entropy, on the other hand, captures dynamic structures of a time series by analyzing the frequency of specific ordinal patterns or trends over time. Let's define our function p_entropy. It takes the pattern counts we generated earlier as the input parameter. Inside, we use our existing Shannon entropy function to find the raw entropy of the pattern distribution, and then compute the maximum possible entropy based on total number of unique permutations. By dividing the raw Shannon entropy of these patterns by the maximum theoretical entropy, we normalize the result. This ensures our final permutation entropy score sits neatly between 0 and 1, making it easy to compare across different datasets. When we run this function against a sample dataset, a score close to 1 means the patterns are completely random and unpredictable. A lower score indicates a highly structured, predictable sequence. Let's test our function with a practical example. We have defined an array of pattern counts with a very heavy bias. One specific pattern appears 50 times, while the other only appears once or twice. This massive variation in frequency means the underlying time series is highly structured and repeating the same trend over and over. This is the exact opposite of a chaotic random system. We pass this highly unequal array into our new p_entropy function and print out the result to see how our normalization logic handles a predictable sequence. When we execute the cell, we get a permutation entropy score of approximately 0.28. Because this number sits so close to 0, it confirms that our data is highly organized and predictable, proving our metric works exactly as intended. And that wraps up our guide to permutation entropy. Now that we can measure how predictable our data is, we are ready to take a look at statistical complexity. We will combine our entropy scores with Jensen-Shannon divergence to help tell us the difference between pure random noise and true complex structure. Please like, subscribe, and I'll see you in the next one.